चालू कर दी।
एक मिनट। हाँ, नहीं
सत्या सर, गुड मॉर्निंग।
Yes.
गुड मॉर्निंग सुनील।
Yeah.
How are you?
So we'll begin.
Yeah. Okay.
First, I will give an introduction of today's speaker. ये इंट्रोडक्शन थोड़ा मराठी में दूंगा, हिंदी में दूंगा, मराठी, हिंदी, इंग्लिश। आज के जो हमारे वक्ता है डॉक्टर बी सत्यनारायण, इन्होंने अपना बीटेक जो है वो इलेक्ट्रॉनिक्स एंड कम्युनिकेशन इंजीनियरिंग JNT यूनिवर्सिटी हैदराबाद से किया और PhD उन्होंने फिजिक्स में किया IIT बॉम्बे से। अभी वो डिपार्टमेंट ऑफ हाई एनर्जी फिजिक्स TIFR में काम कर रहे हैं। 1983 से ही इज वर्किंग देयर एंड करंटली ही इज साइंटिफिक ऑफिसर H, यानी सबसे हाईएस्ट पोजीशन हम मान सकते हैं इसको। एंड ही इज कोऑर्डिनेटर ऑफ INO प्रोजेक्ट, कल जिसके बारे में थोड़ा और डिस्कशन हुआ। ही इज ऑल्सो विजिटिंग प्रोफेसर एट अप्लाइड साइंस डिपार्टमेंट ऑफ द अमेरिकन कॉलेज मदुरई। उनके जो विशेष रुचि जो है वो डिटेक्टर्स एंड इंस्ट्रूमेंटेशन फॉर हाई एनर्जी एंड न्यूक्लियर फिजिक्स एक्सपेरिमेंट्स, जिसके बारे में काफ़ी जिक्र होगा ये भाषण में। सत्यनारायण सर ने करीब 250 रिसर्च पेपर्स पब्लिश किए हैं और नेशनल और इंटरनेशनल जर्नल्स और कॉन्फ्रेंसेस में ये पब्लिश हुए और बहुत सारे इनवाइटेड टॉक्स भी उन्होंने दिए हैं। उनका पहला ही जो पेपर था उन्हें बेस्ट पेपर अवार्ड मिला इंस्टीट्यूट ऑफ इलेक्ट्रॉनिक्स एंड टेलीकम्युनिकेशन इंजीनियर से। और अभी उन्हें भाभा अवार्ड इन साइंस एजुकेशन एंड HBSE 2020 ये गौरव से उन्हें सम्मानित किया गया और उनका नाम जो है वो AICT INAE डिस्टिंग्विश्ड विजिटिंग प्रोफेसर करके मनोनीत हुआ है एट सिम्बायोसिस इंस्टीट्यूट ऑफ टेक्नोलॉजी पुणे। सत्यनारायण सर इज अ फेलो ऑफ इंस्टीट्यूशन ऑफ इलेक्ट्रॉनिक्स एंड टेलीकम्युनिकेशन इंजीनियर IETE एज वेल एज इंस्टीट्यूट ऑफ इंजीनियर्स, बहुत दोनों प्रतिष्ठित संस्थाएं हैं। ही इज ऑल्सो लाइफ मेंबर ऑफ इंस्ट्रूमेंट सोसाइटी ऑफ इंडिया ISOI as well as member of Indian Physics Association IPA। इन्होंने काफ़ी नंबर्स, इनके अंडर काफ़ी स्टूडेंट्स डॉक्टर और मास्टर्स थीसिस किए हैं। अंडर ग्रेजुएट के भी थीसिस इन्होंने कई गाइड किए। He has served on many doctoral and expert committees as well as academic councils, board of studies and advisory boards on colleges, universities and many national organization of eminence। वो हमारे एडिटर भी रह चुके हैं एंड रेफरिंग टीम ऑफ सेवरल प्रेस्टिजियस जो इंजीनियरिंग जर्नल्स है उसमें भी वो रेफरी करके काम कर चुके हैं। ही इज ऑल्सो अ सीनियर मेंबर ऑफ IEEE, जो सबसे प्रतिष्ठित संस्था है इलेक्ट्रिकल एंड इलेक्ट्रॉनिक्स इंजीनियरिंग की अंतर्राष्ट्रीय। एंड करंटली ही इज एग्जीक्यूटिव मेंबर, काउंसिल मेंबर, कमिटी मेंबर and he is the chairperson of IEEE बॉम्बे सेक्शन, जो एक बहुत बड़ा सेक्शन है जिसमें महाराष्ट्र, गोवा, ये सब राज्य उसमें आते हैं। एंड आई हैड द प्लेजर ऑफ वर्किंग अंडर हिम एज कॉन्फ्रेंस चेयर इन द एग्जीकॉम कमिटी। और मेरा जो अनुभव है उनके साथ वो बहुत ही बढ़िया रहा। एकदम सौहार्दपूर्ण तरीके से वो हमेशा प्रोत्साहित करते हैं सभी को और जो भी वॉलेंटियरिंग वर्क है उसमें वो हमेशा चाहते हैं कि सबसे बढ़िया काम हो और स्टूडेंट्स के साथ उनको काम करने में बहुत बड़ा लगाव है। तो इन्होंने एग्जीक्यूटिव कमेटी मेंबर और वाइस चेयर करके भी IEEE इंडिया काउंसिल में, जो पूरे इंडिया की एक काउंसिल बनती है, उसमें काम किया है। और IEEE बॉम्बे सेक्शन का आउटस्टैंडिंग वॉलेंटियर अवार्ड 2014 का इन्हें मिला है। एंड IEEE हेडक्वार्टर से, यानी इंटरनेशनल जो है, उन्हें एमजीए अचीवमेंट अवार्ड भी मिला है 2016 को। तो ऐसे वक्ता आज हमें मिले हैं और मैं बहुत खुद को मुझे बहुत अच्छा लग रहा है कि ऐसे एक वक्ता को आज आप सुनेंगे who is a master in his subject as well as he wants to outreach as many people as possible। तो हम चाहेंगे कि ये लेक्चर जो है वो बहुत आप ध्यान से सुनेंगे और इसके ऊपर जितने भी प्रश्न आपके मन में है वो प्रश्न पूछकर आप आपकी जिज्ञासा जो है वो उन तक पहुंचाए और he will definitely answer, although he has clarified that most of the lecture will be in English and Hindi, लेकिन आप सब थर्ड ईयर के स्टूडेंट्स हैं तो मुझे नहीं लगता इसमें आपको कोई परेशानी होगी। लेकिन जो भी आपके सवाल है वो हम सब लेंगे और उसके बाद हम शुरू करेंगे। तो शुरू करना है। So I welcome you, sir, once again, and now I request you to take over and have the presentation as well. Thank you, sir.
Yeah, thanks very much, Sunil. It was a wonderful introduction, probably not so frequent one get to hear. It's indeed my pleasure. Of course, I would have really loved to come to VNIT in person, and maybe it would have helped a better interaction among with you. Unfortunately, I am myself on an office work here in Madurai, not in Mumbai. So it is getting a bit difficult to, of course, come across. Yeah, so it's always pleasure when we are tied up, when we are together working in a voluntary organization like IEEE, and it was indeed my pleasure to have worked with you for a year and a half or so. Yeah, that's so nice of you for a kind introduction. So can I go ahead and share the screen?
Yes, sir.
Okay, all right. Okay, I hope you can.
Yeah, we can visualize it, sir.
See the screen and yeah, as mentioned by Professor Sunil Bhatt, I kind of had this little distinction of getting trained both in instrumentation, electronics, and also a little bit of physics because my PhD topic has been in the high energy physics instrumentation, which also deals with what we call detector physics, the way the sensors and detectors work. So you will actually find a good flavor of how the detectors and instrumentation are crucial for doing a front-ranking science. But the way I would take my talk to is one is to kind of go through major, what generally they're called mega science experiments that India is currently engaged, both in India as well as abroad. What I meant is some of these experiments were built or being built or operated within India, our own country, or some of them, the collaborators, Indian collaborators have gone to outside, whether it is in Europe or US or wherever, and contributed enormously to the front-rank physics that is being done there. Okay, but in this process, I would specially emphasize the fact that what kind of, okay, while it is true that all these are being done for, as I said, for kind of looking at some of the outstanding problems in science, some of it, I'm sure yesterday, Professor Amol Thige must have mentioned to you, at least in one sector called so-called neutrino physics. But what I want to kind of also say, while the main motivation for these setting up such large experiments involving a lot of money and a lot of people is trying to understand the fundamental, I would say, the laws and fundamental physics or fundamental science in general. What is that is there for, let us say, for students per se, in terms of opportunities to engage on research along with the researchers in the field. And also, of course, you can't suddenly obviously go and start doing research. So what kind of training opportunities that exist on these mega science projects for, let us say, Indian students? Now, when I say students, maybe today I will try to have a little more bias towards engineering students than maybe science students, just because this particular event is being organized by VNIT, which is predominantly an institute of technology. So I will probably give that more flavor than science. But of course, you are welcome to interact with me after the talk for other questions as well. So that is what a slightly longish intro and to what I'm going to kind of do. I hope I'll do justice to what I said and what Sunil expected me to deliver this. Okay, so this particular picture, which is my first slide, you all have seen many, many times, I'm quite sure. You also know a bit of this, why, what is Big Bang, and so on and so forth in the popular media. Now, why I'm showing this picture is because this was, of course, designed by some of us, essentially trying to kind of superimpose, juxtapose these experiments that I'm going to talk to you today, and the fact that these experiments are actually, looking at different time scales of what happened over the Big Bang, from time equal to 0 to all the way to, let us say, 14 billion years now after the Big Bang. So these labels that you see, the logos that you see at the bottom, it corresponds to a kind of mega science experiment that we are going to talk. But since the time is limited, I'm not going to go and explain too much of physics that these experiments are going to do or are they doing, but I'll kind of main points of why the motivation for these experiments are going to, I will mention about. But मेरा main emphasis होगा on engineering details में, instrumentation details में, क्या engineers ऐसा बड़ा बड़ा experiments के लिए, mega science experiments के लिए कुछ contribution कर सकता है क्या, या contribution करेगा तो कौन सा contribution. और मैं एक दूसरा बात भी आपको बताने वाला हूं कि नॉर्मली ऐसा होता है कि साइंस अलग है, टेक्नोलॉजी अलग है, इंजीनियरिंग अलग है, मैथमेटिक्स और डिफरेंट फील्ड है. ऐसा नहीं है, कभी कभी नहीं. मोस्टली इट हैपेंस दैट टेक्नोलॉजी एड्स top ranking science, and science actually helps technology to grow and make new technologies, engineering skills available. ये interconnection जो है between so-called science, engineering, technology, and mathematics. Mathematics are not going to deal much today. Also, I want to kind of emphasize what you see in this picture is starting from, as I said, from the very beginning of what happened at 14 billion years ago. And you can see that there is a time scale that is given here, which is as early as 10 power minus 43 seconds, right after the Big Bang, to today, which I said is about 14 billion years ago. Obviously, the temperatures at that time, this is in Kelvin, are very, very high, and the whole universe has actually cooled to where we are today. At the same time, the energy in the universe at that time is extremely high. And today, as the temperature cooled down, the energy imposed in the universe is also kind of came down. And as the temperatures kind of go by, or temperatures kind of keep decreasing, you also saw that there are different physics that happens in the beginning. The so-called neutrinos, which Professor Amol Dhagia talked about, existed around that very early universe. So this experiment that Professor Dhagia explained is something which is probing at the earliest after a Big Bang. And you must have all heard about CERN, looking at a little later what had happened, how all those particles reactions between one to another. By the way, those little particle names are actually embedded here. It is a neutrino, antineutrino, and so on. Here you can clearly see quarks and Higgs boson and various bosons and so-called bosons, and as well as quark, etc. They're all given here. What happens with the interactions? A little later, a few minutes later, you will actually see another experiment coming up and looking at how the first nucleus formed. And 100 billion years ago, suddenly, after the Big Bang, you will actually see how the first stars are formed in the universe, which is being probed by the so-called square kilometer array, and the structure of entire universe, as early universe as we are seeing, that happened about 500 million years ago. This experiment called 30-meter telescope is going to probe this. And similarly, what happens in the sun, which is giving light to us, again, this must have been mentioned yesterday by Professor Dige, the so-called thermonuclear fusion is actually probed by, in fact, used by ITER initiative to generate very clean energy instead of using fusion. Instead of using fission, can we use fusion, which is a more cleaner way of producing energy, and which is always required more and more demand for the energy. So that is ITER is another initiative, followed by the so-called Ligo experiment, about which you must have also heard about it, because of one of these experiments, one of these stations are going to get installed in Maharashtra. So this is the Ligo experiments, looked at the black holes and how the stars merge, producing the gravitational waves, which are very, very tiny, but they are actually recorded on the terrestrial laboratories, means on the Earth and so on. Now, you can really see that it's very interesting that India is engaged in literally the entire time span of what has happened from zero to now. So that is very interesting. That itself is very interesting. But as I said, I'm going to go through very, very quickly one after the other. But I mainly want to kind of emphasize on the engineering role, the instrumentation role, the spin-offs, the applications of how one such technology used to kind of do physics of a particular type also finds extensive applications for societal applications, industrial applications, and so on, which is not necessarily to directly deal with the science itself. So this is going to be my theme today, right? But just one very basic principles in as simple language as possible, if I can kind of tell you. For example, if you see on the left, you'll actually see lots of objects. It could be entire universe and maybe Earth or a person or let us say a DNA molecule or virus or quarks, nucleus, and so on. Their right side is the one from the biggest object to the smallest object. On the left side, you'll actually see various instruments. They're actually used to observe or probe or measure. Okay, so for example, if you want to observe universe, you're going to use, let us say, telescope like a Hubble telescope. If you want to observe virus or molecule, of course, you are going to kind of use a microscope. But if you want to observe or measure something as tiny as quark, which is a building block of matter, you are going to kind of use these so-called huge accelerators that are available both in India too. We have a specific type of accelerators, but very, very high energy accelerators are available outside. Now you see the observables on the right side and the instruments that you need on the left side. So there are different types of instruments are used for observing different things. But one common principle you should kind of know, doesn't matter what you want to observe in the universe, the probe radiation for using which I want to observe something should be obviously much smaller than the object that I want to observe itself. Okay, this is what is called Broglie wavelength. So for example, if I want to probe what is inside an atom, right, molecule and an atom, then मुझे एटम का क्या साइज रहता है, रफली अबाउट 10⁻⁻10 मीटर्स रहता है. सभी यूनिट्स हम नॉर्मली मीटर्स में रहते हैं. और वो प्रोब एनर्जी जो है, वो जो एनर्जी में जिसका यूज करके मैंने प्रोब कर सकता हूँ एटम का, वो लाइक एक्सरे फॉर एग्जांपल, दैट हैज टू बी ऑफ द ऑर्डर ऑफ 10 keV. But and you can see if I want to observe nucleus which is inside an atom, obviously I need higher energy. और न्यूक्लियर के अंदर भी जाना है, न्यूट्रॉन या प्रोटॉन का स्ट्रक्चर देखना चाहता हूँ, विच इज ऑफ द ऑर्डर ऑफ 10⁻⁻15, मुझे 100 MeV का कुछ इलेक्ट्रॉन का बीम चाहिए. मैं अभी बता रहा था, इंडिया में भी बीम्स अवेलेबल है, सर्कुलर एक्सेलरेटर्स अवेलेबल हैं. वो इलेक्ट्रॉन एक्सेलरेटर्स, इलेक्ट्रॉन सिंक्रोट्रॉन बोलते हैं, जो इंडोर में है. और भी अंदर जाना है, quark produce करना है, whose dimensions are another 1000 times smaller than, let us say, protons or neutrons. Then I require tera electron volt energy, which is only possible by using accelerators. So आपको middle में मैंने एक scale डाला, आपको actually आप देख सकते हैं dimensions in terms of meters, all the way universe is 10 power 26 meters. Say you can actually see that we are talking about the Big Bang, for example, that dimensions are 10 power minus 34. And you can see we are somewhere here at this moment, we are somewhere halfway through. Okay, so we have a long way to go through if you really want to understand what happened at that particular moment of time. But again, you can see what I said before. On the left side, you will actually see technological objects. You will see instruments. You will see big machines. You will see telescopes. You will see accelerators. These are all technology advances. So this is exactly what I said before. You need them in order to do the physics that you see on the right side. But of course, you know very well, every instrument works in the principle of certain physics, certain chemistry, certain biology, whatever it is, right? So it's the science that accelerates invention of new instruments, okay? So let us go to talk about a few minutes what is called CERN. CERN stands for European Organization for Nuclear Research. I mean, it doesn't match to the acronym because the CERN is actually comes from a French acronym. This is located in Geneva, somewhere at this point, if you can see my laser pointer. But what I really want to see, what I want you to understand is, of course, every organization has something like a mission. CERN is built, it's like a world laboratory is what I normally say, that we want to really understand, like push back all the frontiers of knowledge. All the way going, just now we talked about Big Bang, we talked about many such secrets of nature, which we don't want to kind of probe. And very second point, right away, if you see on the right side, it says, develop new technologies and accelerators, detectors, and which has spun off in terms of invention of WWW, invention of grid, invention of medical imaging, diagnosis and therapy, and so on. You can clearly see this is science, this is technology which is required to do the science. Right below, you also say that, okay, there are lots of applications of this beyond science. And even more important, which I underlined on the right side, you can kind of see that to train scientists and engineers of tomorrow. That is what I said today. That was my title. What kind of opportunities that one have. And the most very, very interesting goal of the mission of CERN, at the last point, you can see, unite people from different countries and cultures. I mean, it has nothing to do with science, but science can also bind people and of different culture. So CERN has literally, you can look at these numbers here, thousands and thousands of scientists coming from all over the world, 60, 70 countries. They come there and actually do, one kind of physics that can really open up something new windows for our understanding. So this is the magnificent place where there is a 28 kilometers ring around two countries. I say two countries because you can really see that this side of the thing is actually France, and there is a dotted line. You can really see this is Swiss and this famous Swiss Geneva Lake. And you can see that in this ring, 27 kilometers, I'm actually going to accelerate protons, one direction, another clock and anti-clock direction, and make them collide with each other exactly at the points which are marked here called CMS, in which I worked some time ago for about 10-15 years. And there is an experiment called LHCb, there is another experiment called Atlas, another experiment called ALICE. In India, from India, scientists are working in ALICE as well as CMS. Of course, we are not working on these two experiments, but Atlas and CMS put together has discovered what is called Higgs boson. Some of you must have heard of as a God particle sometime back, and I will actually talk to you a little later. What CERN says is, I mean, the particle physics, which is something to deal with what is deeper inside the matter, is absolutely great pursuit of, completely unimaginable. And now if you want to pinpoint to the smallest fragments, like today we are talking about quarks of the universe, and also you have to build big machines in the world. The biggest machine in the world exists here to do the smallest particle that exists inside the matter. That is just now what we saw de Broglie's wavelength, right? I'm not going to go into giving a lot of details here, but it is a mechanical marvel, if I can use that word, both in terms of what is helped to build this gigantic accelerator, and also each of those big science experiments that are actually built on the periphery or on the circumference rather of this detector. Okay. For example, this accelerator, because you need to provide energy to the protons so that they can acquire more and more energies of the order of 14 tera electron volt energy. Then you require magnets, because protons are charged particles, and if the proton goes past a magnet, then it gets more, energy, right? More moment, more energy. And then like that, if you keep rotating, of course, you will be able to attain the energy that you require. Something like 8.3 Tesla. And, this is also one of the biggest cryogenic installation where helium, liquid helium is used to cool down the entire, the pipe inside to such a high vacuum, I mean, if I can say that, or low pressure, which is even 10 times smaller than what is available in the moon and so on. I mean, you can keep on talking about a lot of details, but let us move forward. Okay. And India contributed enormously in terms of building various components that are required for the accelerator ring itself, and many of those magnets, thousands of those magnets, were carefully tested and installed by Indian groups. Actually, you can see here the Indian collaborators, basically posing with that then President Abdul Kalam and so on. So our contributions to this experiment is quite big. Now, if you want to just look at a kind of a small video animation, you can see what I told you. Now, if you look at a small part where one of those 4 detectors are located, the protons coming in opposite directions, they're going to meet head on. And you can see it's like then they collide and produce much smaller particles, if you like. And they kind of, you can see they're flying away from the so-called point of interaction where they hit each other. And our main goal, the detectors or the electronics, the instrumentation's main goal is to track these particles as they were going through different layers of the detector. So it is like what I sometimes call like an onion peel. So at the center of the onion is where the interaction takes place, and you have many layers of those, and each one of them is able to kind of track like a graph paper where the particles are flying, and I can actually show you this is the path. Why I'm spending time here is to say hundreds of billions of these protons are going to cross every 25 nanosecond. One interaction is going to happen and producing thousands of these flying away from the detector. Now, the techniques which are actually used to do pattern recognition, which in these experiments long ago have become so useful these days on what you today call machine learning, deep learning, neural networks, artificial intelligence. All these techniques have been mastered in this kind of science experiments, and today they are commonplace for many applications beyond science, right? And even the amount of data that gets produced for recording all these tracks that are coming out is of the order of a megabyte every 25 nanoseconds. So I'm actually talking about 40 terabyte of data per second coming out of this. Now you can imagine, we often talk about big data systems and so on. To compare what is the amount of data that any of the social media channels produce, and compare that with the data produced by a single experiment, it's enormous. So that means it is helping us to be able to kind of master these technologies, which are also used in other experiments, other areas, right? So this is just the same picture. I'm actually trying to show like a slice. So the interactions happen here, and these long tracks that you are seeing here are various onion peels that I talked about. And as the particles fly through, they will be able to get recorded very well, just like a snapshot, like a photograph of how these particles are traveling. And we make measurements. We actually measure their energies, of course, the direction, their timings, the charge you call, are they positively charged particles, negatively charged particles, and so on and so forth. Okay, so there are one experiment contains so many different technologies all deployed together. Okay, now how big or how small they are. Okay, each of these are gigantic. Look at the size right here on the top and look at how much it weighs. Okay, it's like weighing about 14,000 tons. Okay, look at this size. Here is a person standing and giving dimension to the detectors that we have built here. By the way, this is not a complete detector, just a part of the detector which is shown. You can see how big these are and how many kind of electronics channels that kind of required to instrument and so on and so forth. In fact, this particular one of the 4 experiments is the largest international scientific collaboration in the history, which involves more than 5,000 physicists, engineers, technicians, students, and support staff, etc. They come from 200 institutions from all over the country, all over the universe. It's about 50 countries. So you can see everybody kind of pitches in, bringing its own kind of technology. India has produced, and you would have seen this picture before, and we not only made one subsystem of the detector, and we also built a very, I would say, high-tech, detector technologies, sensor technologies involving what is called silicon strip detector. So it requires a very special technologies, and I'm talking about quite some time ago. And so India not only contributed significantly to the accelerator development, but also for the experiment here called CMS. Now, similarly, I will just kind of go a little faster. There are also other experiments also built on the same, I told you. It is even much bigger than the CMS. And again, you can see this person here. And look at this size, 46 meters by 25 meters. Okay, 46 meters is something like 12 or 13-storied building height. Now, that is the kind of gigantic detectors that we kind of build. Of course, this weighs much smaller weight-wise, but volume-wise, it is very big. There is also another experiment, and as I told you, India is involved. This is kind of want to understand, the special state of matter that what you call, quark gluon plasma, which is where the quarks, the particles, the gluons, which is like force carriers, they mix together, but of course they do not become like hadrons, like neutrons or protons, but they kind of mix together. This kind of state of matter, if we want to understand, this particular experiment called ALICE is also designed. It's a smaller detector, but a lot of Indian contributions. You can see here, the Indians have made the entire detectors required to build these major experiments. They also built specific detectors, and not only that, what you today call application-specific integrated ICs are called ASICs. ASICs are electronic devices, electronic chips, which are specially designed for a specific application. And these were all done by Indian scientists. There is also another experiment called the so-called LHC-B, which is also one of the major experiments on the LHC detector. By the way, LHC stands for Large Hadron Collider, that ring that I showed you, which is the accelerator on which you have this major 4 experiments. As I told you some time back, 2 of those experiments, in which one we are involved from India called CMS, another experiment called Atlas, together in 2012 actually discovered this particular Higgs boson, which is one of the, if you see in the so-called standard model of particle physics, you see that fermions and bosons are the force carriers which will make for the particles to interact with each other. And the Higgs boson was discovered in 2012, and of course in 2013, these 3 gentlemen got, Peter Higgs as well as his colleagues got award Nobel Prize for predicting that, for the Higgs boson. It is actually named after him. But if you look at the citation of the Nobel Prize, it says Nobel Prize is given to these gentlemen for their theoretical discovery of a mechanism that contributes to our understanding origin of mass. Okay, Higgs field is supposed to be giving the mass to all the subatomic particles that we kind of see. But not only just for the theoretical understanding, but they say which recently was confirmed through a discovery of the predicted fundamental particle by ATLAS and CMS experiments, as I mentioned to you. So it's very important in physics, no matter how big theory is, you should be able to actually prove, you should be able to measure, you should be able to discover, you should be able to see that happening. Then only the award is actually given, because it's very important to kind of prove it by an experiment. Physics is essentially an experimental field, and to kind of do that, to conduct an experiment, all this, what I've been telling, the sensors, detectors, instrumentation becomes part and parcel. I already mentioned to you something about the technologies that are used in such big accelerator experiments to be able to connect up thousands and maybe sometimes tens of thousands of those dots, because they're made by flying particles out of the detector. How do I connect that all these are one track, all the other ones are other track, and so on? They're actually separated by sometimes few micron gap. Now, I can't really use conventional, track fitting algorithms like straight line fit or parabolic fit and so on. You require learning systems which can learn by themselves to be able to identify and join them the way it happens. Okay, so that is what I already mentioned to you. But not only algorithms, we also had to develop special purpose hardware to be able to run these algorithms much faster than the conventional CPUs. So that is how you will see FPGAs, GPUs, TPUs, etc. become commonplace today when they run very efficiently for the what I call the applications that are involved in image processing, right? So this is the great contribution of such basic science experiments for other applications, like it could be security systems, it could be industrial system, it could be simple medical imaging systems which has developed over a period of time. Now, just one experiment that I explained to you will hosts so many engineering technologies which are listed here. I don't want to even go through that, but the list can start from anywhere: civil, mechanical, architectural engineering, heavy engineering, vacuum technology, superconductivity, magnetic and whatnot, gases, optics. But you also have on silicon technology and signal processing technology, computers, network, every field. Now you can name a field of technology, and they were required to be used in those 4 experiments. That is what made, after 25 years of building such experiment, that discovery. And I want to also tell you that quite a few new technology did not exist in 1983, 84, 85, whatever. When this experiment was conceived, actually those technologies have been invented specially for be able to aid building this experiment. Of course, all those technologies which were invented did not only stay in this science lab, but actually they become something which you and me enjoy today. For those of you who are from the electronics background, I don't want to scare you, but just I wanted to kind of say, of course, when you study electronics in the college, we kind of play with some basic building elements like analog electronics, digital electronics, VLSI systems, and ASICs and FPGAs and so on. But using the same basic electronics, can I really build 20, 30 million electronics channels? Like in our lab, maybe you will give a signal from a signal generator or pulse generator and build some building blocks. Now, if I give you, instead of one channel, if I build 20 million such channels, how do you build electronics? And that is the kind of challenge which I told you. And these experiments require you to kind of build such a very, very sophisticated technology, starting from all the way from the front end detectors to the, the basic signal processing, and then, how you bring the data to the back end, and how you build network of such signals to be able to bring, like it is called a form. It is like a form, means thousands of active devices, electronics are all actually connected together to be able to kind of process the data at a nanosecond level. Nano, of course, is 10 power minus 9. So you have to process all this data coming from the detector channels in 25 nanoseconds. You can imagine, right? So, and it is challenging not only because of large number of channels, it's also challenging because you have to process the data very, very quickly. And that is where you need to invent something which doesn't exist in the industry in general. Okay, so of course, as I mentioned to you many times already, using very, very high-end field programmable gate arrays and programming them not in the conventional VLSI languages like VHDL or Verilog, etc., inventing something high-level synthesis kind of programming modes and using very special architectures is something which is required for being able to kind of measure and monitor all the parameters that are coming from such a science experiment. This again requires fantastic skill sets from engineering students, and they are, after such an experience, they'll go ahead and kind of do wonderful work in VLSI industry and also building many systems which are today are required for the societal existence. Okay, and not just electronics or whatnot. Look at an example I want to show you. This is sheer mechanical engineering, if I can kind of say. This object weighs around, let us say, 12,000 tons. Now, how am I going to move? All these are built on surface, and they are actually being taken to a small pit, which is about 100 meters. You can see there is a well here, and I want to lower that down. So how am I going to kind of push this big object? It's not so easy. Now, people invented the best way to do it is put a small gap below what is called air pad. So if I put, apply tremendous pressure of the order of 20-30 atmosphere pressure, the entire object actually lifts up by a few centimeters, and I can actually very easily, just as if I'm just pushing it, and it will slide like a piece of cake. Okay, so I mean, these technologies didn't exist before. There was no industry in the world which could actually build this. By the way, this whole thing is underground, is about 100 meters below. And now you can see this big object, the way it is being lowered down, right? And this really tells that you require new technologies to be invented to run these experiments. Many of you know World Wide Web. Okay, we all use, without that there is no life. But you also must know, I think you already know, this is not invented by a computer company or a software company, but actually this whole concept of WWW by Tim Berners-Lee actually came up in 1991, working at the same lab which I've been describing to you at Cern. Later, there is what is called farm computing, connecting hundreds and thousands of cheap and inexpensive computers together to solve a very, very complicated simulation or computing is something which came out of such a lab, right? Which is called farm computing. We all now hear about cloud computing. We talk about many such technologies, but the so-called computing grid, which is actually precursor to all these technologies, once again came up at the same experiment, namely the data that is, I told you, something like 1 megabyte of data every 25 nanoseconds. This data is actually used to compute the physics by connecting like a tire 1, tire 0, tire 1, tire 2. And you can actually see this is where the data is produced. And so many countries around have the data flowing in, and another layer of countries where further processing is being done. If I have a problem to solve, I just pose in the grid. I don't even know. I mean, I don't solve it by a computer sitting on my desk, but I just pose into the grid, and grid finds one of the free computing nodes. It takes that job and actually brings that to me and say that, okay, the problem is kind of solved. So you don't even know which computer in the world and which continent in the world this problem is kind of solved. This is the mother of all the cloud kind of technologies that we commonly use these days. And the same pattern recognition techniques that I talked about, the same detectors that very, very finely be able to record those tiny interactions that take place inside the detector, can also be used to produce very, very high resolution images of a patient, so that diagnosis and then treatment becomes very easy. For example, the same semiconductor detector I talked to you about, which is actually segmented. You can see, let us say there are 256 small pixels here by 256 pixels, and this is the silicon sensor, which is also used for detection of particles. When a patient is, instead of an X-ray film, if I mount this device in front of the patient and then send the beam of X-ray, it can give you much higher resolution, because actually I divided into pixel detectors. Each one of them is only about 50 micron by 50 micron. Now you can see a person's wrist with a wristwatch is actually kind of photographed here. So we are all used to what is called, black and white or grayscale X-ray, which is more than 100 years by Roentgen. Today, we have what is called color X-ray, which is thanks to the technologies that are used in those experiments, which I kind of shown. And that really revolutionized today the medical imaging thing, right? And you remember I mentioned to you thousands of scientists work in one single experiment. This is also something which you need to kind of learn what I actually call that as a social engineering. How do you put 7,000 or 8,000 scientists under one roof? They're working under one experiment and still able to kind of, work amicably. Is it not something which is also required these days on how such big corporates can actually run seamlessly and without any problems, working on highest level of, science experiments. So I like this picture just because in literally on one roof, you have thousands of those people who have come from various countries. They speak different languages, measure quantities in different units, but they still, when they build equipment, when they build something, they come there, and when you install, the whole thing works and bringing out a fantastic discovery in science. All these also offer good facilities, as I told you, for training. And you can actually see on the right side, there are large number of research programs, training programs for faculties, for young researchers, school teachers, and also undergraduates like many of you people during the summer programs. And I think it is the best if such a thing is utilized, because if you go there and actually look at what is the niche areas in which such a front-ranking work is done, leave aside for a moment the science part of it, but you will be trained in such a great technologies, whether it is electronics, whether it is computing, whether it is networking, all the branches of engineering. That will be a great opportunity. So you should not miss such opportunities. Of course, India played a big role at Cern, what I just now was describing to you. So these are all various institutes. Of course, Nataraj is our own symbol of Indian tradition, which was actually, this was installed in the Cern campus. This is the main building of one of the labs. And you can see that Anil Kakotkar, our past DA chair and the Cern scientist during the unveiling of this statue. Another important experiment called FAIR, which is a facility for antiproton. This is also very similar to what I described to you. This is also a circular accelerator ring, of course, much smaller in terms of circumference. And here too, Indian collaborators from all over the country are deeply involved. At the moment, they are actually building this gigantic facility. Apart from many other scientific goals which I listed here, and I'm not going to go through that. Please don't bothered by such a slide here, but I really want to tell, sometimes it even, one of the goals of this gigantic experiment is also to address how, all heavy elements that we see all around are actually made in the universe. Such a very fundamental, very important consequential question, right? But again, India played a big role in designing, producing and delivering lots of important components for that accelerator there. And again, I want to bring very quickly to how the technologies that are developed in this FAIR experiment are actually going to be useful for humanity in some sense, right? Okay, so you can really see, of course, like the person, for example, if there is a tumor or if there is a growth, unusual growth in the body, and if it was discovered, it was imaged by what I showed you before, how do you actually use to kind of, cure or therapy, what you call it, kill the bad cells? Now, if you use the X-ray technique, which was actually existing before, and you can see that the radiation penetrates very deep, very big depth, right? Now, on the other hand, instead of using that, if you use ion beam, which is the main experiment that I showed you before, and you can see that actually the peak affecting, area is very narrow. That means I'll be able to kind of only treat precisely the tumor, and I will not damage any healthy cells which are surrounding the bad kind of cells. Okay, so therefore, the tumor or something like that. So therefore, the technologies that were developed during, this is an institute in Germany. Okay, it's also can be used for, let us say, the ion beam therapy, which is not anymore a scientific fiction. I mean, hundreds and thousands of patients have already been treated and in the hospitals which are attached with the science labs. Not only that, for example, since they require huge amount of data computation, the technology which was actually used here, what they call green computing, green IT cube, to how do you put thousands, tens of thousands of instruments together and taking care of the thermal management was actually made here at the FIRE experiment. Obviously, all the social media, giants or any other big data centers, the same technique is going to use in terms of, power control or thermal control. Okay. Of course, these techniques are also used, like in the case of recent or right now we are going through pandemic, how quickly one can make the new drugs and vaccines. For that too, people use the same, the beams that I showed you, the accelerators that are told, that's the same tools that are used in the applications to study the so-called proton structure. Okay, analyze the proton structure, and the same ones are also used in medical research, pharmaceutical research, so that drugs can be made much, much quicker than the conventional technique. So the technique that was used for particle physics may be something else, but that is also used for understanding many biological processes and also, how the disease develops and how it is cured and so on and so forth. Just like the other experiment, this also uses, allows, training of large number of students from all over the country. This is again another opportunity for many of you to go and do internships. Okay, the experiment in which I'm again involved currently, and also Amal Dige mentioned to you, it's called India-based Neutrino Observatory. So which is I'm wondering if I can show you. So this is as you can see on the left side, it is a huge 5-storied building, like a detector made of largely iron. It weighs 4 times large. It is 4 times larger than the biggest detector that I showed you at Cern some time back. And you can also see the blue box, okay, made of 50,000 tons of iron, is actually going to be magnetized and making the world's largest electromagnet. And the animation that you see on the right is how the detector is built, literally, plate by plate, brick by brick. The entire thing is actually done. We are planning to do somewhere in Tamil Nadu. By the way, that is where I'm right now sitting and talking to you today, right? So this is, I'm actually on a visit to Madurai on related to this particular experiment. Okay. So what is it that this experiment is going to give? We design our own electronics chips called application-specific integrated ICs, about which I already talked to you about. And our engineers build such chips here, many of them, in fact, dozens of varieties of them. And then, we make our own electronics. We don't, of course, go and buy from the market. Generations of such chips are actually produced within the collaboration. This is a great opportunity for, training or otherwise for engineers around. We use field programmable gate arrays to process about 4 million electronics channels data. Very, very faint signals that are coming from detectors need to be built and processed. Okay, we use, and when we build such kind of boards, it's very interesting to see. This is an electronic board, but which like a very funny shape, like not like a square or rectangle, but it's like a triangle, just because we want to build and integrate a lot of logic into a small segment. So we take an FPGA, put a lot of logic inside, and we build microcontroller units inside, and also other ASICs and all that come in one board. And this board, which is only a size of a pencil, can actually process data coming from 256 lines, actually 128 channels coming from the detector. You can imagine such kind of electronics you don't get to learn when you work in any industry. But when you come to science labs, these are the challenges, and many times, as I told you, we invent new technologies. But is this science also useful outside? For example, if in the current days of international security and safety, people carrying contraband materials to outside across the borders, can we detect that if a truck is carrying such kind of contraband materials, can we find out, for example, if somebody in their truck carrying outside there are, let us say, bananas, but inside they're carrying some, let us say, reactive waste, can we find out? Yes, we can. By using the same kind of detectors that I talked to you about, placing them like a portal when the truck passed by, using the particles which are abundantly available in the nature called muons, I'll be able to kind of track and tell you whether somebody is carrying a safe material or somebody is going to carry some dangerous materials. We can monitor the activity of volcanoes as they erupt by monitoring the activity in the belly of volcanoes by using the same cosmic ray muons that you talked about, and use these detectors which are actually used to do basic science. But then you can actually give a warning to people saying that, look, there seems to be a different activity going on in the belly of the mountain. So therefore, there is likely of an eruption of a volcano. These are all applications sometimes required. If you want to study some archaeological structure without breaking them, of course, right? Like if I want to know what is inside a pyramid, you can use the same detectors and techniques that we use to be able to kind of give you like an image, right? Like an image of what is inside. So archaeological applications. And I also mentioned to you about the imaging, and I've shown you something before, but the so-called positron emission tomography, which is already exists, of course. All the hospitals are kind of equipped with this, but the modern detectors that some of us work, in fact, incidentally, our own experiment, we built what is called resistive plate chamber, a kind of detector. He is actually now making the PET imaging devices cost much lower so that it becomes affordable for even small towns around, right? And you can really see by mounting such kind of small ring of detectors around the patient's head or somewhere, you will be able to kind of find out what are the kind of activity that goes on inside, or there are some tumors that are getting developed. And then, once you know exact location, you can use those imaging, the proton therapy techniques to cure them and so on. Yesterday, probably Professor Amol Dighe must have kind of alluded to how neutrinos can also be used for a societal applications. People are now talking about the next best technology that is going to come up after RF for communication is going to be neutrinos, because neutrinos will not be stopped by any amount of matter on the way. So therefore, I can actually shoot neutrinos from one end of the earth. They can go straight line of sight to the other side of the earth, need not go to a satellite and so on for communication. Who knows, maybe 20 years down the lane, one of you probably will be a person working on neutrino-based communication technologies. Apart from that, of course, neutrinos are also used for many other applications, and I don't have time to go over that. And there are a lot of opportunities for many of you to work in the neutrino labs, and same like as a research scholar or as a summer or winter internship. I think it will be a great opportunity for many of you. And apart from that, I think I have another 5 or 7 minutes probably I have to take. Sunil, can I take another 10 minutes?
Yes, sir. Yes, sir.
Okay. Okay. Let me go a little faster. I'm sorry. I think I was a bit slow in the beginning. This initiative that I talked to you about, International Thermonuclear Experimental Reactor called ITER, this is actually an attempt to be able to produce clean and very safe energy and nearly unlimited energy. Okay, not using fission, which is actually used, the process is used in reactors. So this is supposed to be one of the biggest challenges in our civilization. I mean, you can really look at this is just a prototype facility that is coming up. So, I mean, came up in Germany, but you can, sorry, France, but you can really look at the complexity that it can involve, and India again plays a big role in this research. Okay, so basically, what is actually being done is, can I take, for example, deuterium plus tritium, which means these are the two isotopes of hydrogen. I will want to heat to them millions, 150 millions of degrees Celsius, and then that, of course, it becomes like a plasma, which is actually shaped and confined by magnetic field. Now, so you can't put such a plasma of that high temperature in any vessel, right? The whole thing, of course, melts. So magnetic field is used to be able to confine it like a vessel. Okay, and the helium nuclei, of course, can sustain such a big, very high temperature burning plasma. And then the neutrons which are there, they transfer this energy to outside, which is a blanket, just like you do it in any conventional generator, steam generator, etc. The heat that is produced through the blanket is actually used to, let us say, run some turbine or alternator, etc. And the rest of the process is same as electricity. Now here you don't do any radioactive processes, so therefore it is safe, it is environmentally responsible. So therefore, and no emission of like your thermo other fuels, no CO2 produce thermal electric, producing initiatives and so on and so forth. And it is absolutely a safe way of producing power. So that's why a lot of attempt is being made in these reactors. Okay, so again, India made, as I said, major contributions to this big facility that you already saw. And if this really comes out and become a reality after 10, 20, I don't know how many years, and that will be the greatest contribution that science has made to, in the process, of course, you develop thousands of technologies, but that is the biggest that you can think of for humankind. The Ligo experiment is something which, as I told you, of course, this is used, basically the setup was, two such setups were in United States and also in Italy, one of them, in Japan, another one. And one such setup is actually coming to India as well. It is under construction. So this is again a huge fundamental science project looking at the gravitational waves produced by merger of black holes, which was predicted in 1905 by Einstein. But that is one part of it. The part that I want to emphasize is this is a 4 kilometer long tunnels in which you actually send a laser beam here and they travel perpendicular to each other. And if there is any, let us say there is no vibration that you see here, the reflected beams get added, processed along with the injected beam. If there is no displacement, the signal is going, there is no signal because it gets cancelled away. But if there is a small variation that you see, you actually add up that, you will actually see the tiny signal, the difference between the transmitted and reflected laser beam. And that is the signal for you to kind of sense that something millions of kilometers away is actually some such small process or simple, very tiny signals are produced when the black hole got kind of two black holes kind of merged together. And that sitting on the ground, you are able to kind of monitor them or measure them. And that has actually been, again, one of the biggest new technology. Simple technology, but the precision at which the instrumentation could be developed, it actually helped you to kind of discover this in 2016. And just like Higgs boson 2017, the gentleman who actually predicted these gravitational waves or actually built this instrument also got the Nobel Prize. So, and it is amazing kind of detector. So the precision that you are talking about is something like measuring 40 trillion kilometers of an object with an accuracy of better than a human hair. We are actually talking about measuring quantities which are as small as 10 power minus 21. So this requires fantastic technological outputs, and that technologies which are developed this project find very, very high level of societal engagement, whether it is lasers, whether it is optical components, very, very high. The entire 4 kilometer rings are going to be vacuumized. You can imagine what is the total volume that you need to make into a vacuum, just like those rings that you saw at the Cern. Sensor technologies was a major update, material science, material engineering, computation, and so on. So all these have actually resulted from one basic science experiment called LIGO. I want to give you one more example of an experiment, something talking about black holes, how it can kind of help even for a broken bone therapy. Normally broken bones are joined by picking up a bone from other part of the body of a patient. And then, you do all this, transplantation. But what people could do is using the stem cell biopsy and this particular technique called Nanopic Reactor, which is a result of a technique which is also pioneered in this experiments, where very, very precise nanoscale, absolutely small vibrations are used to promote bone formation and growth from patient's own body. You don't have to really do any transplantation. That has today resulted in what is called, I mean, instead of taking out bone from another place, you actually grow the bone using stem cells with this Nanopic bioreactor, which is a technology I told you, which was actually a spin-off of the Ligo experiment. So where is black hole and where is broken bone? Those are the kind of applications. There is also another major mega science experiment, which is again operating in Himalayas. It's called MACE, which is actually looking for gamma rays which are produced in the upper atmosphere. While studying those, they required a gigantic kind of detector. You can actually see the size of the order of about 21 meters, 356 meters square in the area, which is actually built in Ladakh and operational. Of course, it's again, as I said, basic science experiment. What is that? That is for us, it is in terms of the photosensors that were developed on Indian soil by Indian industry, which you can actually see this large, like a mirror. So you have, hundreds of those, actually thousands of those pixel-like detectors is actually spreading the entire area here. And you can require not just R&D that is done by science labs, but also industry comes in a big way. And today, when you talk about COVID, many of those photo detectors have become commonplace, either for, let us say, the so-called real-time PCR or antibody testing, X-ray or CT imaging. Today, we talk about what is called digital pathology. All these technologies are spun-offs very quickly coming from the photo detectors that were built by industries like this, which were earlier they used to use only for high energy physics or nuclear physics or astronomy and so on. And today they become commonplace in the hospitals. Okay, and many of you have nowadays these oximeters, etc., are also devices which have become big weapons in your hand to fight corona. But remember, all these technologies were mastered as the photosensor devices which are used in basic science experiments. Okay, and I didn't want to go too much detail in this, but the neural networks which have become major part for fighting COVID in terms of CT scan, technologies are also in some way, as I mentioned to you, are used routinely for the track reconstruction in many of the high energy physics experiment. SKA square kilometer array is a big expansion of the radio astronomy instrument that some of you know. It is somewhere near Pune. It's called National Center for Radio Astrophysics. Now they are embarked on a much bigger experiment in 2 continents, in South Africa and Australia, and almost maybe 30 times higher kind of collecting area than the GMRT, which itself is an engineering marvel. And of course, this is an experiment that is in process of construction. And the amount of data that they need to kind of deal with, you can really see like your Facebook, like your Google or YouTube or all these. And this is the kind of data sizes that you're talking about. And you can compare what kind of data that experiments like SKA has to deal with. Obviously, the techniques that you develop are going to become commonplace tomorrow in the computer science and the data science domain, right? The last one that I want to tell you is also very interesting experiment which wants to answer questions like how and when the universe came into being, how did the galaxies take birth, and very fundamental and very important questions. This is again jointly done by India, playing a major role. It's an optical telescope, the world's largest optical telescope of 30-meter diameter. It is expected to come up somewhere in Hawaii. But Indian engineers, students, and researchers built this magnificent instrument. You can really look at it in terms of the size, how big this telescope is vis-a-vis the India Gate and Qutub Minar. These are instruments, highest levels of precision. They actually 100 times probably much better efficient than the largest telescope that you kind of see. And some of the techniques in the process that scientists use, so-called simulation techniques, have become useful in engineering applications, climatic change, computational biology, and even financial technology to predict the risk that is involved in the financial instruments and so on. It's not just physics, but the applications that they develop in terms of Monte Carlo simulations, they're called. Nowadays, every big project, when they actually design and before it goes into construction, you actually do a lot of simulations on it using the same techniques that are mastered in the high energy physics or nuclear physics technologies. A lot of opportunities, as I kept on telling you, this is a facility, you can say a kind of opportunity for students to join in the PhD programs or summer research programs in my organization called TIFR. There is also for younger students and also for faculties dealing with science education. We have a center called Homi Bhabha Center for Science Education, which is also located in Bombay. And there are many, research, Indian Academy of Sciences, there are 3 of them. They also offer hundreds of such fellowships to students and also to the teachers during summer to come and work with research scientists in the country. There is also a center called International Center for Theoretical Physics in Italy, which offers year-long fantastic training programs for school teachers, college teachers, and young students, and so on. You just Google should help you to kind of take you through, and I'm sure you will like the kind of technologies at work or the science at work, and maybe it will motivate you to kind of take up science at a larger scale. So with that, I'm sorry, I think I lost my time, but I want to thank the organizers. I want to particularly thank Professor Sunil Bhatt for giving me this opportunity. I want to end my talk with this nice quote, which was attributed to Einstein. I'm not sure the authenticity of this, but it's very nice. I like this because scientists really do discovery of something which is already existing there, right? You only happen to find a reason for it. But engineers like many of you probably who are there on the call today, you actually end up designing a brand new instrument or build a new circuit or whatever, which never been there before, right? So, but on the other hand, I want to really say, as a literally the bottom line is that if you only do engineering and don't apply science to it, it becomes like a trial and error method. You develop something, the instrument doesn't kind of give you result, you modify, you do a lot of trial and error, and ultimately maybe it will work. But if you, on the other hand, remove engineering from science, it's more like a calculations, it's more like a philosophy, more like whatever. But then, you don't actually go and build something that's going to something work or, something may be useful. I mean, so in a way, science and engineering have to really coexist and I think go forward. And I hope I was able to convince you in the domain of science, experimental science research, it becomes very important that these 2 branches of field of specializations have to coexist. Okay, and at the end, of course, all this we do it is because in some way they also help the humanity ultimately. Thank you very much.
Thank you, Satya sir, for a very entertaining lecture and educative lecture, because both these are very rare to find in one. So with your great slides, you were able to tell how science and technology help each other and in turn help the humanity. So that is I think everyone here has enjoyed this. And there are few questions that people have WhatsApped me. So I will ask those questions. For example, this particle accelerators that you talked in the beginning. So
Yes.
Are these practical particle accelerators made in India as well?
Okay, that's again an excellent question that was asked. This is one of the complex particle accelerator requires several many technologies all in one. Okay, I went through a little fast probably, but the thing is, when you build a big cavity which is of the order of kilometers, and the entire thing need to be under vacuum, and I told that the vacuum is 10 times lower than what you see in the moon. Why this is? Because when you accelerate a particle, you don't want any other particle sitting there and which will come and hit the particles of projectiles, you call, no? Projectile is something which you want to use it to kind of do things. So, so therefore, that is just one technology. Second, you want to, for acceleration of these particles, you need to kind of, give a kick. That means, as the particle is coming in the ring, you need to, every rotation, you have to put more energy into that device. How do? You need magnets, magnets which are all mounted all around. Okay, they sequentially energize. They change the direction of the beam because you can't go straight. Okay, you need to monitor the things that are happening inside. You need to also have other parts in terms of what is the right material for building some of this. So there are challenges. So right now we don't have so-called hadron accelerators too much in India. For example, the synchrotrons that I talked about are electron accelerators, which not protons, but they accelerate electrons. But that is also extremely useful for material science and biological applications and so on. And it's a very successful program, and they're actually planning to build a new generation of synchrotron. In TIFR, you also have not the circular ones, but a linear ones, straight accelerators, which accelerate heavier ions, but not like hadrons, like protons, neutrons. So there do exist accelerators in India, built in India, but not the kind of energy or the complications or different kind of projectiles that you need to be built in, like how it happened in United States or Europe or Japan and other places.
Okay. Some of the questions are on LHC.
Okay.
So Pranav Doshi is a 9th standard student from Somalwar School. He is asking what should be the power to use LHC?
Yeah, I mean, power means electric power, you mean?
Perhaps he's talking about that.
Okay. Well, of course, I mean, I don't have a precise number to give you at the moment, but obviously you require probably, several thousand, or I can say megawatts, several tens
megawatt
power, because there are so many gadgets, so many instruments spread over about 30 kilometers, and each of the detector itself will require about half a megawatt or even more. One detector. Like that, there are 4 of them. So it will be easily several mega watts of power.
Right.
Yes.
Another question is from Rudra Pratap. He is student of VNIT. He is asking perhaps about what are the types of collisions in LHC?
Yeah, so this is again an interesting question. So here you look at the particles, let us say, involving the projectiles involving protons. So obviously these are mediated by strong forces. Okay, and so most of the physics centered around strong force in the LHC. But if you go to, let us say, some other experiments or some other kind of experiments like what we are doing here, as I told you, the neutrino physics involving neutrinos, which are not hadrons, but they are leptons. That involves mostly what you call weak forces, because the interactions are mediated by weak forces. So the physics that happens LHC mostly is the strong.
One more question is from Adarsh Kumar from BHU. He is asking about the energy of ion beam, which used in ion beam therapy.
Okay, this particular slide is referring to ion beam therapy.
Yeah.
Okay. So see, what happens is in most of the cases, when you talk about these, whether it is mass or energy or let us say even distance and temperature and whatever, all these things actually they're interchangeable thanks to at least 3 major equations that we all study, right? I mean, Einstein's MC square, Boltzmann's energy with Boltzmann constant and temperature, and Planck's energy with wavelength and speed of light, and so on and so forth. So one often kind of talks about when you talk about energy, or we talk about different units, okay, if I can say that. So as I mentioned in the very beginning, when I said what is the kind of the principle of probing and so on, we said that, for example, if someone wants to study of the order of atom, that's enough when you want to do therapy and so on for tumors, etc. So one talks about few tens of keV, kilo electron volt, of X-rays, for example. That is the kind of energy that is typically used to penetrate into human flesh and only damage the tumors and not the surrounding cells. So few tens of keV.
Okay. There is one question from Nisarga. He is a polytechnic student, but he is interested about how this experiment will help us to know the age of universe.
Age of
these experiments. Yeah.
Okay. No, I mean, if you recall what I said in the very beginning, probably my first slide, so what one is kind of saying is that, for example, by studying the processes, somebody asked just now about the various types of interactions and let's see what happens and so on. By studying the process that would have happened or the particle that would have existed at some points of time, what you are actually literally doing is inching towards the starting point, which is T0, for example. Now, if you say that, for example, just to say the neutrino experiment that I also briefly mentioned today, it tells you that there are, so as close as almost immediately, you can say T equal to 0. I actually said 10 power minus 43 seconds and so on and so forth. So if you study those neutrinos, which are actually supposed to have existed at the time of Big Bang, and since neutrinos do not interact easily, so they don't kind of, get transformed, get interacted into some other matter, they're just lying, they're just scattered around us still. They're called relic neutrinos which still remain from Big Bang. Now, by studying them, you will probably able to estimate what existed at the temperature or the energy or those levels at that moment of time. And now, if I'm able to look at not only look at the neutrinos, but also measure their energies at that point of time, maybe it will give me an idea, give me a clue, like a snapshot of the existing ones at that moment of time. So, but they are signatures. They are signatures that are going around. But can you really use, the existing detectors to be able to kind of measure them? That's why I try to give an example. Like, for example, 100 years later, when you are able to measure the gravitational waves produced. I mean, gravitational waves were produced hundreds of years, but you had the technology to do it to the level of what it requires today sitting on it. Then only you are able to kind of look at what happened at that point of time. Similarly, today you may not be able to have that precision of the detectors and experiments to measure neutrinos produced, let us say, at Big Bang and so on. But it's a matter of time before people understand how to do it, how to calculate, how to measure, how to distinguish between one type of neutrino to the other type, and so on and so forth. So I think it is a matter of, that is how the kind of science develops. It is not something that you can do right away, and it is inch by inch. I told you something like we are halfway through from now, I mean, where we are to what we understand last 14 billion years. I'm sure it is a matter of time before we inch forward and know what is the age of the universe.
Right. One more question was about the Cern experiment. You mentioned about 27 kilometers. So is that the dia or is that the periphery?
Perimeter.
Periphery.
Perimeter.
Okay. And what is its total cost of Cern project?
My God. Easily $1 billion. Okay. I should say billions of dollars actually. But that's where that question brings me a very interesting thing to kind of share with you. Imagine this experiment actually came into concept in 1983, around that time, early 80s. Okay, the experiment was switched on in 2008. So there's 25 years it took for, as I told you, thousands of scientists to design. Some people worked in physics, some people worked on instrumentation, some people worked in computing, and so on and so forth, to be able to kind of have an idea about, for example, simple thing, I will ask you a question. 1983, you are sitting there and you are actually talking about collecting, let us say 1 megabyte data per 25 nanosecond. 1983, you didn't even have a Pentium, right?
Right.
You didn't even have a proper PC, forget about Pentium. Now, how do you know in 2008, what kind of machine is going to be available to you to be able to use for computation or data storage? People are able to kind of visualize those. And that is how the whole experiment was designed. Of course, as I told you, hundreds of countries were involved. So the amount that I told you came as a collaborative kind of, sometimes we call in kind. In kind means we work towards that experiment. Of course, countries also contribute in cash, in money. And all put together, there are what are called member states. Member states is like, Cern, particularly is a European organization, right? So therefore, all the countries contribute, but today it is a world lab from US, from India. We are also so-called associate members. So therefore, it's a special status. We are not members yet, but for all outside Europe, like US or India, etc., they are associate members. So the money gets contributed from each one of those, not and over a period of 20, 30 years. So, but billions of dollars. That is for sure.
Yeah, I think it must be more than budget of some nations.
Some nations. Oh yeah, sure, 100%. That's right.
Yeah. And finally, I would have one more request to you. Since this was a very interesting talk, explained very nicely in English. Give me a permission to make a voiceover in Hindi or Marathi for it.
Okay, absolutely.
So we can circulate this more in schools and colleges as well, so that they understand it in their level, of course.
More easy.
Exactly more technical, but at least they will be knowing about what we are doing in these mega science and what is the scale of it. So
sure.
Permit me to do voiceover.
Absolutely. Of course, this I must also take this opportunity to thank. I did in the last slide, it was there, but obviously other than CMS and INO, in which I was collaborator myself. So, but other experiments, all the material was actually taken by my collaborators freely. So I am also thankful. So it is not my own material, most of it. So for educational purposes, it's absolutely no problem at all on granting them.
So thank you, Satya sir, for being with us and giving this little bit long but very interesting lecture.
Yeah, I'm sorry.
Thanks a lot, and look to interact you in person sometimes in Nagpur.
Sure. It is my pleasure. Thank you so much.
Bye.
Thank you.